Hello, welcome back. So in this lecture we will be discussing the topic of stability, specifically stability for the systems represented in state space form. It is a very important topic that we have covered already, a couple of definitions of stability when we were discussing the transfer functions. And here we use the same definition of stability, but we look at the systems defined in state space form and see how we can analyze the stability of that. So if I have a system represented at x dot equals ax, and remember that the stability, even when we were discussing the transfer functions, this stability was an inherent property of the system, so it wasn't really dependent on the input. So same situation here, that's why I don't have this plus bu. So if I have the system x dot plus ax, everything about the system, the inherent dynamics of the system is encoded in A. And the takeaway of this lecture, I'm throwing it up front, is that this system is stable. And this is a stability in the sense of Lyapunov, if you remember. One of the definitions of the stability, this system is stable if all eigenvalues of, maybe I should put it, eigenvalues of A, eigenvalues of A, still are, no, half, used to be half, have negative real part. So if all the eigenvalues, real or complex, doesn't matter, if all the eigenvalues are on the left plane, left hand plane in the complex plane, the system is stable. And kind of going back to the idea of the phase portrait. So we saw that these eigenvalues are the directions that are kind of pushing the system, trying to contain it. And the direction of this containment is the real part of the eigenvalues. So if they are negative, meaning that they are pushing the system back toward the center. So if your system is in this direction, because the real part is negative, the derivative is going to be in the opposite direction. So that's kind of an intuitive reason why this should make sense. But in maybe 10-15 minutes of the lecture, we'll see mathematically why that makes sense. And to do that, let's start with a very simple case, a very familiar and simple case that I have. Let me see, what is it? X dot equals ax. Just one state and a scalar equation. So a is a number, x is another number, is a function. So if you remember, the solution to this differential equation is that x of t equals some constant c, depending on what is the initial condition, e to the at. So the derivative will have some a, and what the initial condition is could tell us what c is. So this system, this behavior is either this, if a is positive, or this, if a is negative. So you can think of this differential equation as a matrix equation, but just a one-dimensional matrix. And in that case, it is a matrix of A, and A is the eigenvalue of this one by one matrix, and you can see that if this eigenvalue is positive, your system shoots up to infinity, becomes unstable, but if A is negative, your system converges to zero. In other words, the system is stable. So let's take this analogy that the response looks like that for a system like so. And now let's move to the matrix version of it. So I have x dot equals ax. And similar to this case, that x of t was a constant times e to the at, the same situation holds. So x of t, which is now a vector, so x is x1, x2, x3, and so on. This one equals a vector v, a constant vector v, e to the sum lambda t. If you plug this, so v is a vector of, maybe let me write it down here, v1, v2, and so on, e to the lambda t, and lambda is just a single number. So if you take derivative of this, you will get, because these are constant, they can all be moved out of the derivatives. You will have lambda e to the lambda t as a derivative equals a constant matrix A times, again, same thing. So this can work as a solution pending what are the values of v and lambda. So to know which values of lambda and this constant vector v work for that system of equations, we can plug in this solution into the differential equation. So I'll have x dot, which is v, big matrix, big vector v lambda e to the lambda t. That is my x dot equals a times x, which is v e to the lambda t. So if I can find the right values of v and lambda such that this works, that is the solution to my differential equation. So what I have here is this e to the lambda t is same on both sides, and obviously not always 0, so I can cancel these out. So what I have is lambda v equals av. So v and lambda has to satisfy this property, which now you remember this is the same definition for eigenvalues and eigenvectors. So for this equation to work, I will need to have, I'm going to write the other way because I'm more comfortable, a minus lambda I times v equals 0. So this should hold. And now you can see the solution to a differential equation x dot equals ax is some v to the lambda t, where lambda is an eigenvalue of a and v is an eigenvector of a. So to solve this, obviously we are looking for the solutions where v is not 0. If it's 0, so you get x equals 0, a trivial solution. So v, for some non-zero vector v, if you want to have this equation to hold, this means this matrix that multiplied by v is a weird one. So you have a non-zero v multiplied by a matrix, you get 0. What the hell? So that means this matrix has some issues, and that issue is that the determinant of a minus lambda I should be 0. And this is the polynomial equation that we can solve to try to find the eigenvalues or lambdas. This one is also called the characteristic equation or characteristic polynomial of matrix A or of the system. So we can solve this to find the eigenvalues. And remember that if we have an nth order system or nth order A, this is going to be an nth order polynomial. So I have n solution for lambda, or I have n eigenvalues, some of which may be repeated, and some of them may come as complex conjugate pairs. Let me see if I'm missing anything. So one other item or point to remember, that from this equation we can find the eigenvalues. So I have n eigenvalues, lambda 1 to lambda n. And associated with each of those, I can plug it here. So I have a minus, for instance, lambda 1I times v equals 0. I can go and solve for these individual components of v through a system of equations. But remember that because this matrix is a weird one, we call it, it's not full rank, and it has determinant 0, the solution for v is not going to be unique, and you'll have infinite choices. For each lambda, you'll have infinite choices of v. But one thing you can do is just pick one of those, and all of these v's will be just along the same line. So they are going to be just a factor, a scaled version of each other. So you can choose any one of those, and that would be your eigenvector associated with that. So you'll have n eigenvector and for simplicity, for instance, you can take for any of these v's, take the first value or first element to be equal to 1 and calculate the rest using this system of equations. So when you have identified all these eigenvalues and eigenvectors, so you have n choices of this shape. So v1 e to the lambda 1t could be one solution. v2 e to the lambda 2t could be another solution. And the summation of them could also be a solution. So in general form, the general solution for this differential equation is v1 e to the lambda 1t plus v2. I'm missing. Let me do this. C1. So a linear combination and the nt. So a linear combination of all these possible solutions can give you the full answer, and the constants C1, C2 to Cn depend on the initial condition, where you leave the system and start the system from that point. You can find it by, well, at time t0, all of these e's go to 0. You can find what is the combination C1, C2, and Cn that gives you the initial x value. So this is a full solution. And let's get to something like this. Maybe I will run out of space, but let's see. I'll do this. Let me see if I have anything missing. No, good. So, as I mentioned, some of these lambdas could be repeated, and some of them, maybe more importantly, some of them come in complex conjugate pairs. So if you have one of your lambdas to be a complex number, another one, maybe lambda 2, is also a complex number, but complex conjugate of that. So if my lambda 1 is some sigma plus j omega, my lambda 2 will be lambda 1 complex conjugate, which is sigma, let me call it sigma 1 omega 1. Yeah, sure, why not? Minus j omega 1. And the same way, if I have two complex conjugate eigenvalues, v1 and v2 will be complex conjugate 2. I'm just going to write it as so, that v2 equals complex conjugate of v1. So if v1 is a vector of all complex numbers, the real part of those will remain the same, but v2 will have the minus version of all the complex or the imaginary parts. So having that in mind, I can write this, my x of t is going to look like something like this. So I have v1. What do I want to write? v1. This one is e to the power lambda 1 t plus v bar 1 e to the lambda 1 bar t plus e to maybe v3, sorry, v3 e to the lambda 3t, and so on. So if I have a real eigenvalue, the corresponding solution will look like that. A pair of complex conjugate eigenvalues, the solution will look like this, and the rest of them will be either complex conjugates, pairs, or real ones. So they look similar to those. Now what I can do is write lambda 1 as so have v1 e to sigma 1 plus j omega 1 t plus v bar 1 e to sigma minus j omega t plus v3 e to the lambda 3t. And now I'm going to break these summation in the exponent to e to the lambda 1 times e to the j omega. So I'll have v1 e to the sigma 1t e to the j omega 1t plus v bar 1, yes, v1 v bar e to the sigma 1t e to the minus j omega 1t plus v3 e to the lambda 3t, and so on. And now I can factor out this e to the lambda 1t. So I have e to the sigma 1t times v1 e to the j omega 1t plus v bar 1 e to the minus j omega 1t plus v3 e to the lambda 3t plus so on. to do this. And this part, so e to just an imaginary number, e to the j omega t. This one is, sorry, cosine. This is the Euler formula, so this one is cosine of omega 1t minus j sine of omega 1t, and this one is cosine of omega 1t plus j sine of omega 1t. So now I have v1 times cosine plus v1 times j sine plus v1 times cosine plus or minus v1 times j sine. So I'm going to factor out the cosines and sines. So I'll have e to the sigma 1 t sigma 1 t times, so cosine of omega 1 t times v1 plus v bar 1 plus j sine of omega 1 t times v1 minus v bar 1 plus that one, because I don't have a space I don't write it down, plus this. And now this gets more interesting because v1 and v bar 1 are complex conjugate pairs. So if you add them together, the imaginary parts cancel out. All what I will left with will be 2 times the real part of v1. So I'll have e to the sigma 1t times 2 real of v1 cosine of omega 1t plus 2j and v1 minus v bar 1. So now I have flipped everything in v bar. So now the imaginary parts of the two are equal, but the real parts are the opposite of each other. So the real parts cancel out, and I'll have only the imaginary part. 2j imaginary of, and okay, let me write it down. This is j imaginary of 2j sine of omega 1t. This is going to be j imaginary of v1, because imaginary is just a real number, so I have to multiply by the j plus that, and I'm getting to the end of it. It's not very important, but let me finish it. So I have e to the sigma 1t, maybe 2, I factor out the 2 as well, 2 e to the sigma 1t real of the eigenvector v1 cosine of omega t minus, now I have this j squared with a minus, sine of omega 1t imaginary part of vector v1 plus, now let me write it down to finish it, plus v3 to the lambda 3t and the rest of the terms. So, okay, where are we? Forget about all of that. What we are left with is a combination of exponential terms in the final solution of x of t. So let's zoom out. What we are doing, we are solving this differential equation. So I calculated the eigenvalues and eigenvectors. I could write x of t as a linear combination of eigenvectors times e to the eigenvalues times t, blah, blah, blah. I get to here. So if my eigenvalues are real, I keep them as this form. And remember, these are constant numbers, constant vectors. If my eigenvalues are complex, I can take the real part of it, sigma was the real part of eigenvalue, and then multiply by something that oscillates back and forth. And this is a real number that just oscillates. So long story short, I have these exponential terms that are either the whole eigenvalue, if it's real, or only the real part of it. So in both cases, if the real part of the eigenvalue is negative, I'll end up with exponential functions that decay over time, and either this oscillatory behavior or this constant vector, the effect of them diminish over time. So if the real part of these lambdas, lambda I, are negative, I have exponential terms that eat into all these other behaviors, and the system will be stable. Long story short, that. So, okay, this was a little too much, maybe. I wanted you to see this, and I encourage you to pause the video and take a moment, revisit what happened all here in these steps, so you know what is going on, why the eigenvalues define the stability of the system. But, well, pause. And at the end of the day, we get to this statement that we can analyze the stability of the system defined by matrix A by looking at its eigenvalues. If all of them are negative, the system is stable. Maybe I can write one more thing here. And unstable if even one of the real parts of the eigenvalues is positive, the entire system will be unstable, because there will be one of these exponential terms that will blow to infinity, although the rest of them will diminish over time and go to zero. That single one will remain and will just keep increasing. So that will make the system unstable. All right, so I have covered a lot of stuff. Let me clean up the board. I have a little bit left, and I will come back. Just to quickly recap what we have. So the solution to a matrix differential equation x dot equals ax is going to look like something like this, with a bunch of terms related to complex eigenvalues and a bunch of terms related to the real eigenvalues. So I just want to visualize, help you visualize what these things mean. So remember, V1 in this case, let's focus on that, is a vector of complex numbers. So I'm taking the real part of all those numbers in each element, and that forms a vector. I can draw it. So this is the real, a vector that is represented by the real parts of all the elements of the original vector V. Same with this one, the imaginary part of V1 is also a vector of real numbers. So imaginary part is a vector of real numbers. And what is happening is I have this vector, and that vector. I can draw it in my state space. What is happening, each of these is multiplied by a cosine and a sine. So similar to the sine and cosine in a unit circle that was going around. So as we change the sign, we go around this circle. So your sine increases and decreases over the x-axis, and cosine increases and decreases over the y-axis. So the same situation happens here. Multiplying this vector by cosine, essentially I'm going back and forth along this axis. And multiply the other one by sine, I'll go with just 90 degrees change. I go over back and forth over this direction. What really this term in parentheses means, I am, as time goes on, I go around an ellipse that is that passes through these 4 points, and I just keep rotating about that ellipse. And when multiplied by this e to the sigma t, the real part of the eigenvalue, depending on whether it's positive or negative, either I go around and eventually converge to 0, or go around and start making bigger and bigger ellipses until the system blows up. So this is why we have these ellipsoid shapes of the system in the phase portrait that looks like an ellipse. And now you can see how they are the response is related to the real and imaginary parts of the eigenvector that define the shape of this ellipse. And when you have only real eigenvalues, not complex, so you will end up with a real eigenvector that is a direction. And as you start from any point along this, if your eigenvalue is negative, you start from here and come down in the same direction towards 0. So these two are the general modes of the system, modes of the response of the system, depending on whether the eigenvalues are real or imaginary. And this is something we saw before too in the phase portrait. So in this particular example, you can see on top that eigenvalues are complex conjugates, and the eigenvectors, the two columns are the two different eigenvectors. They are also complex conjugate pairs. And those are the ones in the phase portrait plot depicted. The real and imaginary ones are the ones depicted by the colored, the green, yellow, blue, and purple directions. And you can see they form the shape of the ellipse around which the system response is rotating, and with a smaller and smaller radii until it gets to the 0. And I wasn't going to show you, but let me show you this. Sorry, I have to step out of let me increase this to 0.1. And this is what happens when we have these real eigenvalues. Where did it go? A little bit more. Okay. If I have my eigenvalues, both of them real, so I don't see these kind of rotations anymore. I only have these two directions that are shown by the yellow and purple lines. Those are the two eigenvectors V. And if you leave the system anywhere along those directions, you just follow the same path toward the origin. And if you start somewhere off, anywhere else on the plane, essentially the response is a combination of these two, and depending on what are the values of your eigenvalues lambda, the strength or the speed by which the system converges to 0 is going to determine the behavior. Let me take a look. So here it is evident that the system is converging towards zero along the purple line faster than converging towards zero along the yellow line. This means the size of the eigenvalue associated with the purple is bigger, and I have a faster convergence towards zero. Okay, that was another thing I wanted to show you. And the last item on my list that begs the question. So we have seen the stability in the state space determined by the the real part of the eigenvalues, which must be negative, before in the transfer function domain. We also saw the system was stable, stable if the real parts of the poles were zero. These were the poles of the system. Poles. So you can kind of try to think and ask this question: are they the same thing? Are they not? Were they similar? What can we make sense of it? So another thing to remember, I had x dot equals ax, characteristic polynomial was determinant of a minus lambda I or I lambda I. It looks nice. A minus lambda I equals 0. When we had the transfer function equals y over u or x, let's call it u. The characteristic polynomial characteristic polynomial was denominator equals 0. This gave us eigenvalues. This one gave us poles. And if real part of this was negative, real part of this was negative, that one was stable. If real part of this was negative, that one was stable. So are these the same thing? The answer is yes. That if you have a system represented by this and transform it to transfer function form. Remember, we had the concept called transfer matrix, which was the matrix of all the transfer functions from all the inputs to all possible outputs. The poles of all those transfer functions will be the same as the eigenvalues of A. And I'm not going to prove it, but intuitively, you can think of it this way, that at the values of lambda, where this is 0, something goes wrong with the system. If the denominator is also 0, something goes wrong with the system. So these are same things that goes wrong, causes the same situation, same problem to the system. Maybe if you want to see it a bit more mathematically. So let's start with this. I can take this is a vector of x dots, a constant matrix S, A times by a vector x. So I can take Laplace transform of individual, essentially, lines of that set of equation. What I'll end up with is S x of s. So x of s is a vector of Laplace transformed of all the state variables. So this one is x1 of s, x2 of s, and so on to xn of s. This one, taking Laplace of the other side, A is again a constant matrix. Let's keep it as is, times x of s. Let me see. Let me add another thing here, because this system now doesn't have input. Remember that the stability is an inherent property of the system. It doesn't depend on the input, but let me add another BU. Add this. Now if I keep going, and B is a constant times U of S. So I'm going to try to relate these two forms together. And for the sake of simplicity, assume that y of s is the vector of my states. So I'm essentially measuring all the states as outputs. So doing that, now what I can do is take this to the other side. So I don't know whether it's better to use y of s. Let's use y of s. So I have si. Let me take this to that side. Oh, no, take this. Si minus a times y of s. So I'm replacing x of s with y of s because I'm pretending y's are the outputs, equals b u of s. And assuming that this is invertible, I can take the inverse of that. I can take the inverse and multiply both sides by the inverse of this matrix. So I have y of s remain on this side, and si minus a inverse b u of s. And my transfer matrix is y of s over u of s equals si minus a inverse b. Now you can see kind of where things are going. So this is a matrix. This one. It's somehow a matrix. Let's call it matrix A prime. So if you want to take inverse of that, I'm going to continue here. So si minus a inverse. How you can take inverse of that is a long story, but it is going to be 1 over determinant of si minus a times something called adjoint matrix of that. And now you can see where things start to shape up. So my y of s over u of s is 1 over determinant of si minus a multiplied by something. Adjoint of s times this b, and another matrix, let's call it a prime. And these are just numbers and polynomials. This doesn't have any fraction in it, just a bunch of numbers and s's. And when I multiply this scalar value to that matrix, individual elements are going to be multiplied by that. So now you can see the denominator of the transfer function is actually the same equation of si minus a. If this one equals 0, we can either say it is the equation for the eigenvalue, or because it's a denominator, we can say it's a characteristic equation that gives us the poles of these transfer functions. So the determinant of this, well, essentially this equation, is the linking between the transfer function and the state space equations. That's why this, and well, I have raised it, the other one, the real part of either poles or the eigenvalues has to be negative to have stability. All right, so I think that's all I have for now. You can now easily analyze the stability of linear systems using either the transfer function terminology or state space terminology. They are more or less equivalent. On the one hand, we call the stuffs of interest eigenvalues, and the other side we call them poles, but they are the same thing. Okay, that's all for now, and when we come back next time, we'll look at a small other stuff, including the vibration analysis of multi-degree of freedom system, and a little bit of the time history or the time response of the system in this state space form. So until then, I'll see you.